Hello everybody. For the next section here, 11.1, we're going to take a look at what's known as a cross-section. So first step would be to define it. We're looking at the intersection of some plane parallel to the base of a three-dimensional solid. So we're going to basically take a slice out of each picture at some angle. As long as it's parallel to the base, that's going to be how we end up getting an actual cross-section. So consider the cylinder here. We've got 3 copies of it. We're going to have a good comparison of whether or not it is versus is not a cross-section here. The base of your cylinder would be the 2 circles that are on the ends of it. If we take this slice out of it, we actually get a circle which is directly parallel to either end. So in this case, we actually do have a cross-section. If we take it at a slight angle, we'll end up with an ellipse, or if you want the layman's term, an oval, which means it's not a cross-section because it's not parallel to the base. And if we go across the figure horizontally like this, we're going to end up with a rectangle because we're going to go across one circle, up the other side. We're going to go back across the circle that's on the background and then back down the other side. We're going to get a basic rectangle cutting through it. So we end up with a rectangle, but again, same thing. This is not a cross-section, courtesy of the fact that it's not parallel to the bases. The most common question you get out of what is a cross-section is literally just name the figure that's been formed and determine if it is following this definition or not. So 2 very quick examples. If we take this slice out of this pyramid, we're going to come across the base down here, and we're going to follow along all the way up and then all the way down the other side. We're taking a triangular slice out of this pyramid, so we are getting a triangle, but that is not what shaped the base is. The base is this rectangle down here on the bottom. So it is not a cross-section by definition. But compare that to picture B. If we take this slice out of the picture, we are getting this pentagon drawn across this slice. So we are getting a pentagon, which is exactly what the top and the bottom are, and as a result, it actually is a cross-section. Identifying what shape you get is as easy as it is in these 2 pictures. You just very literally highlight what you have and then give it its proper name. The other common question that we get is based off of a very famous mathematician by the name of Cavalieri, who developed the following principle. If 2 or more 3D solids have the same height, so you'll notice in these 3 pictures here, they all have this same height from top to bottom, and they have the same cross-sectional area at each level, then they are forced into having the same volume. The idea in this picture is if B is the same as B is the same as B in all 3 pictures, then as a result, all 3 of these figures take up the same amount of space. So as far as problems go, all we look at is check if they have the same height. If they do, check if they have the same cross-section area. At that point, we can determine which one's bigger or smaller, or if they happen to be equal. So take a look here at A, 2 different pictures. We have a rectangular solid with a bunch of rectangles shaded in as we go, and this one is clearly triangular prism. We have triangles being tipped into 3D. The first step, though, is to go looking for the height. They are both 20 inches tall, so the first portion of Cavalieri's principle is met. They are the same exact height. Now the question stands, does the area of this rectangle match up to the area of that triangle? And for that, we'll just calculate each one. The area for the rectangle over here would be its base times its height, which in this picture would be 6 inches by 4 inches to end up being 24 square inches. While we come over here to the triangle, area for a triangle would be 1/2 of the base times the height. So we have 1/2 of 6 times the 8, which comes out to be 3 times 8, and therefore is 24 square inches as well. The question was, which figure has the larger volume? They came out to be exactly the same, so neither of them's larger. They actually have equal volumes. One last one here. Let's take a look at B. 2 different prisms, a trapezoidal prism here on the left with all the measurements as you can see, and a square prism, plain old box, here on the right. Same idea though, we go looking for the 2 requirements in Cavalieri's principle. They are the same height, they are both 10 centimeters tall going into the background. So now the question becomes, is the area of this trapezoid the same or bigger or smaller than the area of this square? That'll determine which one has the bigger volume or if they happen to be the same. So we'll check area of each one. The area for the trapezoid will be 1/2 times the sum of its 2 bases times its height. So we end up with 1/2 times, if we go looking for the 2 bases, the top one's blank here, but if you go in the background, you notice the 6 covers that back here, and we have the 12 as well in the bottom one. So 6 plus 12. The height of the trapezoid, if we look at the back one, we notice we have 4 centimeters in the shaded part here. So it is 4 centimeters tall for the trapezoid. At which point we just go calculate this out. 6 plus 12 is 18. Half of the 18 is 9 times 4 gives us 36 centimeters squared. The square is the easy one. Area of a square is literally the side length squared. 6 squared gives us 36 centimeters squared as well. As they came out to be the same cross-section area, they in fact must have equal volumes. Neither is larger than the other, despite their appearances. That's the whole point of Cavalieri's principle. 2 figures can look wildly different from each other, but if they have the same heights and the same cross sections, it's guaranteed they're forced to become the same volume. That's everything for section 11.1. Go ahead and jump into the assignment, and if any questions come up, make sure to ask your teacher, and see you in the next section.